Alright, this is our lecture number 26, I believe, and this is the last topic of the semester, which should altogether complete the picture of the majority of statistical tests that are applicable in pretty much any practical situation. So in this lecture we're going to take a look at the two tests. We're going to look at Wilcoxon Ranksum test and Wilcoxon signed Ranksum test. Okay, so in the last 25 lectures, what we discussed in terms of testing was primarily tests that are associated with numerical data and also nominal data. So kind of, if you think about that, for example, when we started just talking about tests, we looked at t-test for one population and also z-test for proportion, also for one population. And then we expanded that portfolio to include t-test for numerical data for two samples. And we looked at two different cases. Case number one was when samples were collected independently. So sample 1 is random and sample 2 is random, has no connection with sample 1. And the requirement was that both populations, both samples, and populations therefore, have to be normally distributed. The same, by the way, applied for single population t-test, right? So we talked about the fact that you can speak about mean as the most typical representation of your data center only when your population and therefore sample are normally or approximately normally distributed. So when we discussed the two population t-test for independent samples, the requirement was that sample 1 must be normally distributed and sample 2 must be also normally distributed. Okay. Then also we discussed the z-test for proportion differences, and again it was for two population samples, right? I believe the example that we did in class was, oh my god, what was the example? Can't remember right now, quite frankly. It was a long time ago. So, well, let's say for example, oh yeah, it was I believe what we discussed was marketing related, right? So the soap company sells two different versions of soap, brightly colored and dull colored soap, and we wanted to see if the brightly colored soap, same product but different packaging, will grab statistically higher market share. So what we did is we placed two versions of soap in two different supermarkets and asked them to keep track of the sales. So every time when they sell our bars of soap, then we record this as ours. Every time when they sell competitors, we record it at competitors. A, B, C, D, but it doesn't matter, it's not ours, right? And same thing for the supermarket too, where we placed the dull version of the same soap. And our hope was that proportion of sales for brightly colored soap was statistically higher than the proportion of sales for the dull colored soap. So that was the idea. And for that, we used the function prop test, right, to test the hypothesis. But the bottom line was that the data that we looked at was nominal, because each time when bar of soap is sold, we just record, is it ours or is it not ours, right? So it's not numerical, it's categorical, and it's ordinal more specifically. And also, we used t-test for that. So we discussed that we use the function prop test, which essentially implements the z-test for proportion 1 minus proportion 2. Then we kind of scaled it up a little bit. We said, okay, how about we are going to test multiple populations, more than two, at the same time. And the examples that we used in class was, I believe, also from marketing, right? The company wants to advertise the juice concentrate, apple juice concentrate, and they're not sure how to pitch that to the customers. So they had three versions of their commercial. One commercial concentrates on price, another on convenience, and another one on the quality. And what we discussed was the ANOVA test. So ANOVA test allows us to test multiple population means in one test. So instead of comparing them one against another, kind of in a pairwise fashion, instead we can run just one test, and the test will tell us that all the means are the same, or no, they're not the same, at least two are different from each other. And we used the ANOVA test for that one, and the ANOVA test again assumed that samples are independently collected. That is one way ANOVA. And each sample must be normally distributed. That's another requirement that we verified. And then we also discussed chi-squared tests, right? In the chi-squared test, there were two flavors of the test that we discussed. One of them was goodness of fit test, and in the goodness of fit, we test if the population responses, proportions in the population, multiple proportions in the population, are distributed according to a certain preconceived or preset default distribution of proportions. And I believe example that we did was also actually from marketing, fabric softener, right? So there are two major players, A and B, and between them the market is distributed 40%, 45%, and the rest 15% is others, right? And then companies conduct aggressive advertising, and we want to see if after advertising the proportions of customer preferences redistributed. So in other words, percentages of customers that prefer company A, B, or other changed after the advertising campaign was conducted. And this test was about nominal data as well. The difference is that why we use the chi-squared test is we were testing multiple proportions simultaneously. And then we also used chi-squared distribution to see if one nominal variable is independent or not from another nominal variable. Okay, and the simple example that we looked in class was how gender, male, female, affects pet preferences, cats versus dogs, right? So it was about nominal data. So if you look at the test that we covered so far, we only considered essentially two cases, right? Case one was data are numerical and normally distributed, and case two was data are nominal. Well, we looked, we left outside sort of our attention two different cases. Case number one. Alright, so what if you have numerical data but samples are not normally distributed? Then what? And we can't use t-test, and we can't use ANOVA if it's three or more populations. We have to use something else, right? And another case that we didn't even consider yet, what if your data are categorical but not nominal? What if they are ordinal? And the important distinction between ordinal data and nominal data is that ordinal data is orderable, right? In nominal case, there is no order between the categories. There is no natural order between the categories anyway. For example, gender, male, female. There is no natural order between them, right? Which one do you prefer, cats or dogs? Well, data is nominal, but there is no natural order, right? It's not like it's better to like cats and not so good to like dogs, or vice versa. So the important thing to remember, and we discussed it at the beginning of the semester, is that for ordinal data, unlike nominal data, we can calculate median, an observation in the middle, right? That separates 50% of data below that from 50% of data above that, above the median. And that essentially allows us to actually talk about non-parametric statistics. Now, the reason why we call them non-parametric statistics is Pretty simple. When we test hypothesis for the mean, mean is the parameter. Okay, this parameter kind of tells us where the center of gravity is positioned in the data distribution. So it's a representation of where is the center of the data, central location. Well, when data are not normally distributed, numerical data are not normally distributed, then the whole idea of mean as the typical representation of the data center, it's kind of moot point. Here is the good illustration. Okay, so this is clearly an example when population 1, so red and blue, red population 1 and population 2. Both populations, let's say it's numerical data, they are bimodal, right? So there is a bulk of data around this peak and another bulk of data slightly lower around the second peak. So if for such data we'll compute the mean is going to be somewhere around this valley. Okay, so we kind of agree on the point that mean is the, well, center of data, most typical value of your data set. Well then, in this case, mean, what does it represent? We have valley, right, around the mean. We have the valley in the data distribution. That means that if anything, I have few of these numbers, right, in my data set. So therefore, the mean, in this case, cannot be considered as the typical central location where the majority of data are concentrated, right? So therefore, mean cannot be really used as a judgment point for the most typical values in the data set. So hence, I cannot really use parameters, right? So that's why these tests that we're going to consider in this lecture and in the next lecture are called non-parametric. So how non-parametric tests are conducted? Well, if you look at different textbooks, there are actually two ways how we can formulate null and alternative hypotheses, and they're similar, okay? They just sound different. So instead of mean, we're going to use the idea of population locations, right? Sometimes, as an alternative in other textbooks, non-parametric tests are also formulated as the tests about the median. Because if I can't use the mean, then median is my next best choice for the center of the data, most typical central location for my data set. And median can be computed in both cases when your data is numerical and not normal, or when your data set is ordinal. In both of these cases, median can be actually computed. So oftentimes, non-parametric tests are formulated in terms of as a statement about the median 1 versus median 2. Okay, so let's take a look at. We're going to stick with the version about the location of the populations. Okay, so if I plot my histograms for my sample 1 and sample 2, and they look like this, kind of occupying the same amount of space, right? The position along the horizontal axis is the same. They overlap a great deal, two histograms. Then I'm going to say that population 1 has the same location as the population number 2. Okay, what are the other options? So here's option number 1. If I plot two distributions, for example, histogram for numerical data or bar chart for ordinal data, and my sample number 1 is looking like sample number 2, but it's shifted towards the lower values, then I'm going to say that the location of population 1 is to the left from the location of the population 2. So in our old way to formulate hypothesis, it was the same thing to say that mu1 is less than mu2, right? The average for the population, true average for the population number 1 is less than the true average for the population number 2. Or in this case, I can use the median, right? We discussed that a few minutes ago, that instead of the idea of the location, I can use the median, right? So in this case, I'm going to say that median for the population 1 is less than the median for the population 2. Alternatively, this is how things are going to work out, right? My sample 2 occupies lower numbers, and sample 1 occupies higher numbers. So in this case, I'm going to say that population 1 is to the right from the population 2 locations, or, which is kind of alternative way to say the same thing, the median for the population 1 is higher than the median for the population number 2. So, yeah, okay. Therefore, our old way, well, when I say old, that means in previous lectures, right, of testing hypothesis was, we discussed that about mu1 minus mu2, right? And the three forms were mu1 equals to 0, or to, mu1 minus mu2, sorry, mu1 minus mu2 is equal to a number versus not equal to a number, it's greater than a number versus less than, or less than or equal to versus greater than. So that was our old way to test hypothesis, when we could use the idea of the mean, because the samples or their differences were normally distributed. So in this case, mean is the center of the data, rightfully so. Okay. So my new way to say the same thing is going to be, for the case equal versus not equal to 0, I'm going to say that the location of population 1 is different from the location of population 2. So it's the same thing as in my old way of testing hypothesis, mu1 minus mu2 not equal to 0. So mu1 is a different mean than mu2. When in the previous, all these previous tests, I tested mu1 minus mu2 greater than 0, that was my alternative. Essentially, that means that mu1 first average is higher than mu2 second average. Well, now that I'm dealing with non-parametric statistics, I'm going to say that population 1 has the location to the right, so in the area of greater numbers, to the right of the location for the population number 2. And similarly, in my old test, I used mu1 minus mu2 less than 0. Essentially, that means that mu1 is less than mu2. Now I'm going to say, for the non-parametric tests, that that the location of population 1 is to the left of the location of the population 2. So it's pretty straightforward idea that my old way of formulating alternative hypothesis now translates in the new way without use of the word mean, but now I'm using the word either median, or in this chapter actually we're going to use location instead of the mean. Okay. Alright, so these are just three different forms. Okay, so the first form is going to be that null is going to state that the location of population 1 and population 2 are the same, versus no, they're not the same. In other words, that is not the case, right? One distribution is not on the top of another distribution, so that's my alternative. If that is the case, and my population 2, it looks like it's shifted, distribution is shifted to the right, and that's exactly what I'm going to test. My null is going to be that locations of population 1 and population 2 are the same, that's the null. An alternative is that population 1 location is to the right from the population 2 location. And another alternative is like this, okay? Distribution of sample 1 is shifted to the left, and that's exactly what I'm going to test. My null is going to be that population 1 and 2 have the same location, or alternative, population number 1 has the location to the left from the population number 2. Okay. Now, today in this lecture we're going to actually discuss two different tests, but they're done by the same function in our studio. And the test is called, first test that we're going to discuss is going to be Wilcoxon Ranksum test, or sometimes it's also called Mann-Whitney Wilcoxon Ranksum test. Now, important thing to remember, and I'm going to actually illustrate that for you in just 1 second using our analysis flowchart. that Wilcoxon Ranksum test is used in two cases. First thing is it's always used when samples are independently collected. So that's very important. And it's used also for two samples, okay? When we're comparing two populations. Well, we have two samples of data. So I have two samples. Samples must be collected independently. So sample 1 should be random and sample 2 also random. And it has nothing to do with sample number 1. And it applies in both cases when the data are either ordinal or sample 1 and sample 2 are actually numerical. Well, here I have the word interval, but at least one of my samples does not meet the requirement of normality. So I'm plotting the histogram, and then I'm running the Shapiro-Wilk test, and at least for one sample, normality is not the case. It's not normal. Okay. Now, reminder: when we're dealing with independent samples, we have to check every sample for normality. That is the case for two population comparison, and that is also the case for more than two populations, for one way and another. Samples must be normally distributed. So when I'm using Wilcoxon Ranksum test, I have to check each and every sample for normality. And if at least one sample proves to be non-normal, that's a dead giveaway for me that I cannot use ANOVA or I cannot use the t-test, and I have to use Wilcoxon Ranksum test in this case. Okay, so without further ado, let's take a look at this question. Painkillers. I believe in the previous lectures I told you already that the biggest users of statistics are pharmaceutical companies and healthcare industry in general. So the way how drugs are approved is golden standard for the drug approval is something that's called double-blind randomized testing. So what does that mean? That means that we're going to get a bunch of people. So let's say, for example, for this one, okay, for this study, new painkiller. That's a good example. I'm going to get, so a company, drug company is trialing double-blind randomized trial, a new painkiller. So in this case, they selected, actually should be 100 and hold on, should be 120 people randomly, and then we split them randomly into groups because the samples have 120 people, 60 people in each sample, so 120 divided by 2. So we select 120 people randomly and split them in half again randomly. How do we know that the new formula for the painkiller that we came up with is, let's say, better than the aspirin? It's more effective than the aspirin. So the company wants to claim that my new painkiller helps with pain much better than the approved, good old aspirin. So how do we prove statement like this? Well, the idea is that you split the group of people into two subgroups, right? One of them will be given a placebo, and we discussed that placebo is an empty pill, right? So if I want to verify that the drug basically does something, okay, not even comparing to aspirin, it does reduce the pain. So my first test, okay? So group number one gets placebo. So literally, physically, what that means is every person in the group gets a pill that looks like a real pill, but it does not have the active ingredient inside of that, okay? But they don't know what they're taking. We don't tell them. Moreover, people who are giving them the pill, they also don't know. Somebody else actually keeps track of who gets what. That's why it's called double blind. Not only people who are being treated don't know what they're getting, but also people who treat them don't know what they're giving. And that's done obviously so that we can eliminate the factors. If I'm giving somebody a pill and I know that this is an empty pill, I may kind of wink or something like that and say, oh, you poor thing, you're not getting the real thing, right? So something like this, right? So when I'm giving, when it's double-blinded trial, basically it means that people who administer the drug and people who receive the drug, nobody knows if that drug is a real drug or is it empty, nothing, placebo, okay? That's why it's called double-blind study. So I have two groups. One receives placebo, another receives the real drug, and then after that I ask them, right? in this case, when I'm dealing with pain, I can't measure the level of pain in people. I don't have a painometer, right? I mean, for example, if the drug is supposed to lower cholesterol, I don't have to ask them anything really, right? Because cholesterol is measured through the blood test. So I can draw the vial of blood, put it through the the device, spectrometer or whatever, and it will give me the concentration of cholesterol in the blood. Simple as that. Okay, there is an objective measurement. When I'm dealing with painkillers, there is no objective way to measure the pain, right? It's basically how you perceive the pain. So we're asking people on the scale from 1 to 5, tell us what you feel. So 1 means drug is not effective. So I took it and nothing. 2 means, yeah, I feel a little bit less pain, but it's not a whole lot less actually. So it's kind of slightly effective, but pretty crappy, all things considered. 3 is somewhat effective. So it's kind of, yeah, some pain is gone, but a lot of that is still here. 4 is quite effective. That means that I'm almost free of pain. There is a little bit lingering still in the background. And 5 means excellent, extremely effective, pain is completely gone. So again, the responses are subjective, okay? So every time when we cannot measure the effect of the drug by some sort of the device, by the blood sample or the breath sample or something else, okay, then all I have to do is basically ask people, how do you feel on the scale from 1 to 5? Okay, and in this case, I'm not comparing the drug to the placebo, right? So I take 120 people, randomly split them in group 1, group 2. First group receives aspirin, our traditional established painkiller on the market. Second group receives my new drug that I'm claiming is better than the aspirin, and that's what I'm asking them, okay? Everybody receives a pill, it's either my drug or the aspirin, and I'm telling them, hey, asking them, tell me on the scale from 1 to 5, what do you feel? Not effective or extremely effective or everything in between. Okay, so well, let's formulate the hypothesis first. Okay, so what are we really, well, actually, you know what, even before we do that, let's jump to our good old friend analysis flowchart. So and you know what, even before we do that, let's take a look at the data. So that's probably the best approach, right? Alright, so new drug trial data, that's how I'm going to call it, okay? And read CSV, and the file is called, I believe, new underscore painkiller.csv, if I remember correctly. Yes. And now let's take a look at the structure of the data, right? Structure of the new drug trial data. Bam. Okay, so what do I see? I see 60 observations. Makes sense. It's 120 divided by 2. Group 1 gets an aspirin, group 2 gets the new one. And in each group, so I give them the drug, right? And everybody who took the aspirin, I'm asking them, what do you feel on the scale of 1 to 4? So the first person tells me, yeah, it's quite effective. I feel less pain, a little bit still remaining. Person number 2 says, nope, don't feel any different. Crappy result. 3 says, yeah, it's somewhat effective. So I feel half pain gone, but half is still there. 2 says a little bit effective. So these are just different, again, subjective responses, right? And I'm going to do the same with the group that takes the new drug that I'm trying to prove is better than the aspirin. So 3 means quite effective, right? No, not quite, somewhat effective. 5 means it's really good. 4 means it's quite good. So that's how I interpret the results. Okay. I want to point out that first of all, I'm comparing two populations, right? People who take aspirin versus people who take the new formula that I'm trying. And also, samples are independent from each other. Indeed, for the samples to be matched pairs, that means that person number 1 in sample 1 aspirin should be somehow linked to person number 2, number 1 in the second sample, right? What could be the linking factor? Well, it could be, for example, both of them are males, right? So I can compare, because a lot of people are saying that, you know, women are more tolerant to pain than men or something like that. Okay, so therefore, If one would be a guy, another would be a girl, right? That would not be that would be mixing and not affecting the study. So how about I'm going to make sure that participants, matching participants, number 1 and number 1, first of all, they're the same gender, and second of all, they are of the same age, for example, because you know the effectiveness can be different by age as well, right? So I have to match somehow observation number 1 and observation number 1, observation number 2 and observation number 2. My problem doesn't tell me anything quite like that, right? So I get 120 people, randomly split them in group 1, group 2, and that's how I got my samples. So samples have nothing to do with each other, completely random participants, okay? Alright, so let's go to our flowchart. Compare two populations, that's pretty obvious, right? Comparing aspirin versus new drug. Data type, well, on a scale from 1 to 5, but 1 through 5 are not really numbers, they're like labels that I assign to different different categories, right? So and moreover they're ordered, right? Because 2 is better than 1, 3 is better than 2, 5 is better than 4, so therefore I'm dealing with ordinal data. Experimental design, well, I'm dealing with independent samples, and there you go. Here is the answer. I need to use Wilcoxon Ranksum test. Okay, so this is an example of how we can use this flowchart in order to come up with what test we need to use for the specific data in a specific way how the data were collected. Okay, now what exactly am I testing? So let's go back to the slide. Okay, I'm trying to see if drug company is trialing new painkiller, half giving aspirin, and half given the new drug. So I'm trying to see if the question actually is on the next slide. Can I conclude at 5% significance that the new painkiller is perceived to be more effective than the aspirin? I guess I should add that, right? Than aspirin. Okay. So what does that mean? Since new effectiveness is measured on a scale from 1 through 5, right? We just discussed that. More effective means it's 5 and 4 and 3 as compared to 3 and 2 and 1, right? So I have more high numbers in my sample as compared to low numbers. So more effective would mean that, let me go back to my, this is what more effective would mean, right? If I'm saying that population 1, now let's say population 1 is aspirin, let's do it in the alphabetical order, right? I told you that every time when R deals with categories, it lists them in the alphabetical order. So between aspirin and new drug, N, A comes first, so aspirin is going to be my population number 1. Okay, so new drug, that's my population number 2, generally will receive higher rankings, right? I'm going to see more 4 and 5 rankings compared to aspirin. And at the same time, aspirin probably will receive more 1s and 2s compared to my new drug, right? So in other words, my distribution for the new drug will be shifted towards the higher numbers as compared to the distribution of the aspirin. Okay? So this is the hypothesis that I'm going to test, that the population aspirin location is to the left from the population new drug location. That's essentially what I'm testing. Okay? Alright, so now let's go. And this is what essentially I formulated here. Okay? So new drug is to the right from aspirin, or, which is the same, aspirin is to the left from the new drug, right? I can actually formulate it in both ways, right? And my null is always going to be that the locations of my aspirin and the new drug are the same. Okay, so now let's go ahead and do the testing. Alright, so the testing is done. So I established that I have to use Wilcoxon Ranksum test, also known as aka Mann-Whitney, right? Mann-Whitney test. Alright. So testing is done by the function Wilcox, and as I start typing, you can see that Wilcox is one of the functions which is supplied in our Wilcox test. Alright, and I have to supply a couple of things to Wilcox test. First things first, right? I have to supply, and an important thing to remember is the way how I write my hypothesis, which population comes first, that's exactly how I should list that. It's not new idea for us, right? Because when we tested hypothesis for the, when we used the t-test, we did exactly the same thing, right? If I formulate that my mu1 minus mu2 is less than 0, when I call the function t-test, I have to make sure that my sample 1 comes first, mu1 comes first, mu2 comes second, and the alternative is less than, right? So therefore, whichever form I pick, that's how I'm supposed to feed the parameters to the function Wilcox.test. So here I record, and let me illustrate both ways. Okay, so here I record that the new drug is to the right from the aspirin. Okay, so let's go back. So here I'm gonna say, what's my data set? It's called new drug trial data, $ new, right? The second one is new drug trial data aspirin. Okay, the mean mu that I'm testing is 0, the difference is 0, and because my new drug goes first, it's supposed to result in higher numbers, right? So therefore the result is that the new drug is to the right, that means greater, right? Greater. And also just the same as we did for t-test function. Remember when we discussed hypothesis testing for independent samples versus matched pairs. The difference, it's exactly the same way how we call the t-test, right? t.test. But the difference is, for independent samples, I say paired equals false. For matched pairs, I say paired equals true. Same exact thing happens here. When I'm using Wilcoxon Ranksum test for independent samples, I'm gonna say paired equals false. These are independent samples, right? Bam. Okay. So there it is. Alternative hypothesis: true location shift is greater than 0. All right. So my new drug, and here's my p-value, right? The p-value is 7.5 times 10 to the power negative 5. So this is extremely small number, right? So what do I say? Well, I say that my p-value is less than 5%, and therefore I have support for my alternative hypothesis, which means that truly the location of population new drug is to the right from the location of aspirin. Okay, so therefore I have statistical confirmation that my new drug is statistically resulting in less pain than the proven painkiller on the market, which is aspirin. Okay. Crap, I forgot alternative, right? Alternative. Hold on. Alternative equals greater. Let me rerun this thing. Okay. But it did understand what I'm trying to say. So the p-value didn't change. All right. So p-value is 7.5 times 10 to the minus 5th power. Okay. So, and I'm going to try it again, but this time around I'm going to change the columns, right? So first I'm going to feed the function the aspirin that comes first alphabetically. Next one is the new drug, right? But aspirin is supposed to get lower ratings, right, on the effectiveness compared to the new drug. That means that I'm still comparing median 1 minus median 2 versus 0, right? But now my alternative is less than. Aspirin is supposed to get median, which is less than the median for the new drug. That's pretty much what it says. And paired equals false. That didn't really change. So I'm running the same test, really, right? I rearrange the the order of my population 1 and population 2. That changed the form of my hypothesis, but look at that. I'm still getting the same p-value, and I'm still getting the same exact answer, right? I have enough evidence to reject null in favor of alternative, okay, and therefore I do have statistical confirmation that aspirin is ranked overall, all things considered, lower, receives less ratings, lower ratings compared to the new painkiller. So that's my statistical confirmation that new drug seems to be more effective than aspirin, right? And that concludes problem number 1. Now what I want to point out is this. Let me go back to my analysis flowchart. Remember when we started today's lecture, I told you that Wilcoxon Ranksum test is going to be applicable in 2 cases, right? First of all, populations or samples must be independent. That's number 1. Well, actually number 1 is I have to have 2 of them, sample 1 and sample 2, from population 1 and population 2. Number 2, samples must be independently collected. And number 3, I have to deal with either ordinal data or numerical data where at least one sample is not normal. And let me show it to you. So in our case, we dealt with ordinal data, right? Started with 2 populations, ordinal data, independent samples. Here's your Wilcoxon Ranksum test. What if the data that I collected was numerical? And I would go here, comparing central locations, experimental design, independent samples, okay? And then after that, big fat question, of course, how are the samples are distributed, right? Can be normal or non-normal. So I test my sample 1 and it's normal. I test my sample 2 and it's not normal. Then I have to go over here, and both of them are not normal, same thing. At least one has to be non-normal. And what do I see? I see exactly same test. Wilcoxon Ranksum test or Mann-Whitney test. So Mann-Whitney test, Wilcoxon Ranksum, applies in 2 cases. When data are numerical, non-normal, or when the data are ordinal. But it has to be 2 populations and it has to be independently collected samples. Alright? So this example illustrates how to use the Wilcoxon Ranksum test when data are ordinal. Alright, so let's move on. Let's consider one more test, and that would be the end of our lecture. Okay, so when I have matched pairs, then unfortunately what happens is this, and let me illustrate that with my analysis flowchart. When I'm comparing 2 samples, again, it's all about comparing 2 samples in this lecture, okay? And the data are independent samples. In this case, I'm going to use different tests if I have ordinal data versus interval not normal data. So let's see. If I have 2 populations of numerical data and there are matched pairs, and the distribution, so if distribution of difference is normal, then I'm using the t-test for matched pairs, right? We did that about 10 lectures ago. That's old news for now. Alright, but if if I take the differences between matching observations, test them for normality, and it turns out that the differences are not normally distributed, then I cannot use t-test. What do I use? In this case, I use Wilcoxon signed Ranksum test. Okay. All right. What happens if the data are ordinal? Okay. So if I compare 2 populations, data are ordinal, and they're matched pairs, then in this case I use sign test, and that's the difference. Okay. When data are independently collected and they're either ordinal or numerical non-normal, and the test is the same. It's Wilcoxon Ranksum test. But when the data are matched pairs, there are 2 different tests. So if it's numerical matched pairs and differences are not normally distributed, then I'm using Wilcoxon signed Ranksum test. Note the difference. First one that we just considered is called Wilcoxon Ranksum test. if the data were matched pairs, then I would use a different test, Wilcoxon signed Ranksum test. Actually, the only difference in this case would be that I'm going to use the same function in R, wilcox.test, but for the parameter paired equals, I would say true instead of false that I just used. Right, that's the only difference in terms of the code. Okay, but the test is different, really. But if I would use ordinal data, matched pairs, then I would use different test. Okay, so it's not Wilcoxon signed Ranksum test anymore. It's called signed test. All right, so let's go back to our problem. So I use Wilcoxon signed Ranksum test again when I have two populations of data and differences are not normally distributed. Okay, so here, but not normally distributed differences. Alright, that's important distinction. So I don't really test each one of my samples separately. All I have to do is test the differences, right? And the data are matched pairs, that's why I have to test differences. Okay, but the data must be numerical, so it cannot be ordinal. In this case, I use Wilcoxon signed Ranksum test. Alright, so let's take a look at the problem. Some movie studios believe that adding sexually explicit scenes to the home version of the movie will increase the appeal, popularity, and profitability, therefore. So, movie studio executive decides to test if this is true. So, he selects, or she selects, 40 movies which are rated PG-13, so they can be watched by the families, right? Or if you're under 13, parental guidance is advised, right? Okay, so these are more or less family-friendly movies. And then she adds a couple of explicit sexual scenes to each one of these movies, and after that the rating changes from PG-13 to R. But the rest of the movie stays the same, okay? So both versions were made available for renting in shops, so you can tell that this is a problem from good old days when we still had Blockbuster around, where you could rent either DVDs or, even before DVDs, VHS, right? Video home system tapes. Okay, so she places the PG-13 version of the movie for rentals in one set of Blockbusters, but the same movie with rating changed to R into a different set of stores, right? And after that, she records for each of the movies out of these 40 pairs, right? Number of rentals per week. So number of rentals, how many times the movie was rented, that should give you an idea of how popular or not so popular the movie really is, right? And why do we deal with the matched pairs in this case? Because in each line, well, let's take a look at the data first, right? So I'm going to start a new one here. Okay. So here we used Wilcoxon Ranksum test. Okay. And now we're going to use something else. I don't know what it is, so I'm going to leave it mysteriously empty for now. Okay. So movies data. Read CSV, and the file is called C data. I believe it's called R versus PG13.csv. Yes. Okay, let's take a look at the structure. Okay, of movies data. Like this. All right. So both columns are numerical, right? So movie number 1. PG-13 version was rented 772 times. The same very movie, but its counterpart, the R version, right, expanded edition, so to speak, was rented 815 times. Movie number 2, whatever that is, PG-13 version was rented 592 times, and the expanded R version of the same very movie was rented 648. So now I believe it should be pretty obvious why are we dealing with matched pairs, because really observation number 1 and observation number 1 are linked together. It's the same movie, right? Just slightly different expanded version. Observation number 4 and its counterpart observation number 4 from sample R are matched pairs because it is the same movie, same title, right? Just different versions. Basic edition PG-13 and its expanded version R. Okay, so we are dealing with matched pairs, and data are numerical, right? Obviously, because what we measure is how many times they were rented. It's not ordinal data; it's actually numerical data, interval. All right, so let's go back to the analysis flowchart, and let's be formal about that, right? So I'm going to pretend that I have no clue which test to use. So I'm comparing two populations, clear, right? Data are numerical. We discussed that earlier. It's all going to be about central locations in this class, right? So I kind of forget about that branch that says variability. So central locations. Experimental design, we just discussed that these are matched pairs, right? And now the next big question is, do I deal with differences between matched observations which are normally distributed versus non-normally distributed? That would define what should I use. Should I use a t-test for mu1 minus mu2, or should I use Wilcoxon signed Ranksum test? Okay, so it appears that now I have to calculate the differences, right? So I'm going to do the same exact thing what we did when we used t-test for matched pairs. So first things first, I'm going to calculate differences between PG-13 minus R, or vice versa, doesn't really matter. Okay, so how do I do that? Well, I'm gonna say movies data, new column, differences, right? That's how we did it. Equals, and I have to take one of them, whichever comes first, which comes first alphabetically. Apparently PG-13, right? So I'm gonna say movies data, version PG-13 minus the same data set, movies data, the version R. Okay, so now apparently I calculated the differences. Let's verify that structure of my movies data is yes. So my two old columns and the differences. So I subtracted PG-13 minus R, 772 minus 815. Apparently it's 43. Yes, it is minus 43, right? 772 minus bigger number, it's negative. Okay, nice. So now let's, so in order to proceed, what I have to do is decide, are these differences normally distributed or not normally distributed, right? Okay, so let's go ahead and do that. So first of all, histogram. Let's take a look at how the data are even structured. So histogram of the column movies data, differences, like this. Whoa, whoa. If I would have to guess, Shapiro-Wilk will agree that this is not normal. This is so not normal, it's scary. That's probably the scariest distribution that I've seen so far in this class. Okay, so let's take a look at Shapiro test. Okay, so all I'm testing is really movies data and the distribution of the differences. Alright, so I'm expecting to see very low p-value. Yes, indeed, it is very low. So again, I'm testing two hypotheses, right? Reminder, null is that the data are normal versus alternative H1, data are not normally distributed. Okay, all right, so low p-value, 4 times 10 to the minus 5th power. What do I do when p-value is low? I reject the null in favor of alternative, and it says that statistically this picture is not normal. Well, we knew that already. So data, in other words, matched pairs differences are not normally distributed. So I have to go in this route, and therefore I have to use Wilcoxon signed Ranksum test. Okay. But before we proceed with the actual test, let's decide how exactly we are going to formulate our hypothesis. So this is pretty much, on this slide I follow the logic, right? How to find that we have to use Wilcoxon signed Ranksum test by following the flow chart. Comparing two populations, data type are interval, experimental design matched pairs. Why? Because it's the same movie, two different versions. How about distribution of differences, not normal? Bam, there you go. Alright, so what exactly are we testing? Here's what we're testing. If the belief is true and R restricted, right? That's what R means. Restricted movies generate more rentals. That means that if I plot two histograms, right, how many times the PG-13 was rented and how many times the R were rented, R would contain bigger numbers, right? So in other words, the location of population R is to the right. It contains bigger numbers. It was rented more frequently compared to the population location of PG-13, right? So that's essentially what I'm testing. That's my alternative, okay? So, or I can say PG-13 is to the left. So it's R from the right to the PG-13 or PG-13 to the left from R. It's basically potato-potato kind of deal, okay? I'm saying the same thing using different words. Alright, and now of course there is no difference, right? That the locations of R and PG-13 populations are the same. Okay, so therefore, over here, I can go ahead and fill in the blank. So I'm using here Wilcoxon signed Ranksum test. Okay, and as I told you before, right, so here testing using testing Wilcoxon test, right? Wilcoxon test. No, testing Wilcoxon test doesn't sound right. Using Wilcoxon test. Alright, and as I told you before, it's really the same function. Okay, and again, I have to feed the function sample number 1, sample number 2. What is my hypothesized difference between the median 1 and median 2? The alternative, and the only difference is that instead of saying paired samples, paired observations equals false, which means independent samples, I have to say paired equals true, right? So Wilcoxon test. So which one do we want to do first, R or PG-13? Let's go with R. Okay, so I'm gonna say movies data R. Okay, and our hypothesis was that R is more popular, right, compared to the PG-13 version of the same movie, which means that R has more rentals, which means that distribution of R generally shifted to the right from PG-13. So I know which alternative I'm going to test, right? So R goes first, movies data PG-13 goes next, and I'm gonna say difference between the medians I'm testing is 0 and the alternative is greater, right? Because R is greater, it results in bigger number of rentals compared to PG-13 versions of the same very movies, right? And what makes this Wilcoxon signed Ranksum test is this. I'm gonna say paired equals true. Okay, that's the only difference. Alright, so now I'm ready to run this thing. It gives me a couple of warning messages. I'm going to ignore them and pretend that everything is okay. But it gives me a very low p-value again, right? So therefore I reject the null. And what was the null? Null was that the location of R population is the same as the location of the PG-13 population. In other words, statistically, PG-13 versions are rented just as frequently as the R version of the same movie. That was my null, and I reject that. In favor of what alternative? That the location of population R is greater than the location of population PG-13, right? So in other words, R-rated versions of the movie, they do generate more rentals, and therefore they do gain popularity. So what the executive was suspecting about how popular different versions are, that if you add a couple of explicit scenes to the movie, it will increase the popularity and number of rentals. That is actually true. That is statistically confirmed by Wilcoxon signed Ranksum test. Okay, so we are at the 1 hour mark. So I'm going to stop the recording right here, and in the next lecture, which probably is going to be our last lecture for the semester with the new material, we're going to take a look at a couple of other new non-parametric tests, and they are sign test, when I have paired observations but the data are not numerical but rather ordinal. And also we're going to look at the equivalent of the one-way ANOVA, which is called Kruskal-Wallis test.